we're talking about the invisible light that fills the universe. That's part of the electromagnetic spectrum. There's only a small part of that spectrum that we can see. But in fact, because of this vision revolution, we've made all of those forms of invisible light visible.
So we've been looking into light for about 2 years. We've been interested in vision for a long time. We consider that vision is the tool of the artist. We ask people, we make art and we ask people to look at it. And of course, light is the medium. So that naturally led us to being very curious about light. And so we conceived this very vast exhibition and series of lectures or talks that look at all the light in the universe. Yesterday we looked at X-ray and gamma. On Sunday we looked at the whole history of investigation into light.
And the whole theory of light.
And the theory of light. And today we're going to have a look at ultraviolet, which is something, of course, we're very familiar with. I mean, you would be, Denis, having spent many years as a lifeguard, getting your nose burnt.
So we're all aware that sunlight has a lot of ultraviolet. We're aware as well we may not be so aware that ultraviolet is not so different from visible light by comparison to X-rays or gamma rays.
No, it's an ionizing radiation like gamma and X, but it's got a longer wavelength, so therefore it's less penetrating, less dangerous.
Longer than X-rays or gammas, but shorter than visible light. Yeah. So it's got more energy than visible light, which is where the problem comes from, isn't it?
And so that's why it burns. It's got more energy. It can release. It's ionizing, so it can release an electron from a cell, from an atom essentially, which can of course cause skin damage. And this actually is an amazing photograph here. This photograph of a young lady, possibly an Irish lady, under ultraviolet light, where we can see very definitely her freckles.
And more freckles than you would be able to see in visible light. And it reminds you that UV is a form of visible light because there are animals who can see this light.
Yes.
And there's
chameleons.
And we have cameras that can see these. The camera that took this photograph.
That's right.
So it's very similar to the light that our eyes see, but it just sees slightly different things.
It was discovered in 1801 by a German researcher called Johann Wilhelm Ritter. And in fact, Ritter had a short and very tragic life, actually, sadly. He was a self-taught investigator. He was really interested in science. He had been apprenticed to an apothecary at 14 years of age, so he didn't have formal education in science. But he was very, very interested in electricity. And so he spent a lot of time, he was looking at batteries. In fact, he invented the voltaic battery in 1902. Yeah, incredible. By using, electrolyte solutions and attaching electrodes to different parts of his body. So he attached sort of electrodes to his nose or to his fingers and
ran electricity through his body. My goodness, yeah.
So and died, of course, at 33.
And was that anything to do with him dying?
I don't know. It's hard to find out exactly why he died. But
yeah. So aside from the electrocuting himself or passing electricity to himself, he obviously investigated light.
Absolutely. He heard about infrared, the discovery of infrared.
Which was Herschel, wasn't it? We're going to come to that in
That's right.
Lecture 5.
William Herschel.
Lecture 5, yeah.
That's right. Discovered infrared in 1800 and discovered that there was some type of radiation at the end of the visible spectrum that heated things up. That was warm.
So he put a thermometer at the end of a rainbow that had been created by a prism, I presume, a bit like
Herschel. He did, yeah.
And then he discovered it was hot even though there was no light.
That was right. That's right. Yeah. And so Ritter was really interested by this, and he believed in the polarity of nature, that everything had an opposite, and so he figured that if there was heat at one end of the spectrum, then there must be cooling rays at the other end of the spectrum.
So Herschel's discovery was heat rays, wasn't it, at the time? That was, and he was expecting to find cold rays.
Yeah. But he didn't find them. He did a lot of experiments using silver chloride and a variety of other chemicals and discovered that silver chloride darkened. Silver chloride is what you use, on photographic plates. He discovered that.
Did he invent photographic plates?
No, I don't think so. But he was using silver chloride for experiments, and it darkened suddenly. So then it didn't change the temperature. So then he deduced that they were not cooling rays, but he called them chemical rays.
Okay. So what he discovered beyond the violet end of the spectrum was a form of light that was invisible. What we now know is that lots of animals in nature can see parts of this spectrum, especially the closest part. In particular, bees and insects.
Well, bees, chameleons as well. It's very interesting. A chameleon, the chameleon emits ultraviolet radiation. This is the most extraordinary thing. Its skin, but also its skeleton, emits ultraviolet radiation.
No. And is that destined to other chameleons?
It must be, and it will pass through the skin. So, and it's a bluish, and you see that when you look at this image, it's a bluish tint, but that is not a fictitious image. It genuinely is a bluish tint.
So, if there's some animals, let's take for example bees, who can see in the ultraviolet part of the spectrum, presumably they see colours in that region, like the same way as we see blues and reds and greens. They see another colour that we can't see.
Absolutely. I mean, bees see, so humans see from 700 to 400 nanometers, and bees see from 600 to 300. So it's like a whole shift, in fact, towards the ultraviolet edge of the spectrum. So bees don't see reds very well, in fact, at all. They see really much more towards the blue end of the spectrum.
Right.
And they see beyond that area, they see, ultraviolet colours that they perceive, those wavelengths, and they will see them as colour, or at least some type of indicators. But we can't imagine what they possibly are. This is the thing.
And presumably as well, we're talking about a whole nature that's ultraviolet, because if bees are looking at the world with ultraviolet eyes, there are flowers which presumably are beckoning them with ultraviolet colours. But of course we don't know what they see, because these images that we see are just translating those invisible colours into colours that we can see.
Exactly.
And the real question is, you look at the bee here, and you look at the extraordinarily sophisticated eyes, but you also look at the fact that it's got a very, very tiny brain, and all the faculty that we have for appreciating colour and thinking about colours and naming colours.
Well, that's it.
The bee can't do any of that.
I mean, does this look like colour to a bee?
Does a bee even have a sense of colour?
Yeah. Or is it just some type of indicator or a code system?
Because we already have the problem with even communicating between ourselves. If I say to you, what is yellow? You can just tell me it's like a banana or like a lemon, but
So
presumably if I saw lemons as purple, then I'd assume that you're talking about purple.
Yeah, I mean, I think we have that question again and again with people, humans who are colourblind as well. I mean, they see a lot of different colours as shades of grey, apparently. But what even is a shade of grey, really, when you ask it?
So,
it's a code, isn't it?
Do colours exist in nature at all, or is it just in our heads?
Codes?
Or is it just something in the mind?
I really don't know what you think.
If it is just in the mind, can we say that bees have minds? Because one of the creatures that always stands out whenever you talk about colour vision is the mantis shrimp, isn't it?
Well, the mantis shrimp has got so many colours on its shell. It's quite extraordinary. I mean, look at that.
Yeah.
Blues, greens,
so they're
reds,
extraordinary
brown.
in terms of the colours that they can see, and in terms of the colours that they produce, that they can project, and apparently the two things are connected, aren't they?
I imagine so. Yeah.
When they started researching what mantis shrimps actually see, it seems that they're not super sensitive to colours in nature, but a lot of the how many cones have they got?
So the mantis shrimp has between 12 and 16 types of photoreceptors, and we've
Right.
got 3.
Right. So you can
So,
imagine already our field of vision is quite rich, our field of colour.
Incredible amount of combinations that we can compose from those. So the mantis shrimp with 12 to 16. Wow.
And some of them are in the ultraviolet range, and some of them are in the visible range, but some of them are just colours we could never see.
We could not imagine. And the other thing that the mantis shrimp can do is a thing called spectral tuning, where he can change his way of receiving different wavelengths to correlate with his context. Just like
Wow.
incredible. And yet he's
Okay.
got like a tiny brain.
And you know the research that we read regarding what the mantis shrimp sees in the context that it lives in shows that it's not especially sensitive to subtle colours, but the mantis shrimp produces a lot of colours in its epidermis.
So why is that? Why do we think that
And it
is?
seems apparently that those colours are destined for other mantis shrimps who can see specifically those colours, and some of the cones that they have see specifically the colours.
Okay. Because he's
that other mantis
actually,
shrimp.
other than the colours, he's not terribly pretty, is he? So this is
is-
like somebody wearing an Easter bonnet sort of thing.
Oh, from our point of view, it
Yeah.
might be very pretty if we heard the mantis shrimp. And presumably this is something something to do with mating rituals, and presumably it must be something social. I would imagine as well.
So, but as we said earlier, this guy has a tiny brain. So what's he going to do with all of these colours?
Well, that's a big question because clearly they're not being used to the research that's been done doesn't really show that they're able to distinguish colours much better than we can. It seems that it's mostly about communication, and when you think about it, that's really what. We talked about bees earlier, and bees are flowers are producing colours to attract bees, and bees are looking out for specific colours that the flowers that they're going to get honey from will be producing, and that's a kind of form of communication, really, isn't it? Using colour.
Well, it is. It's signalling, isn't it? So I wonder what this those beautiful reds on his hooves mean. And there's like giraffe. If you look at it, those like giraffe spots.
Yeah.
Go back, see there's the giraffe
They're quite
spots there,
extraordinary.
and there's
It's such a mixture of colour and patterns. I mean, it's quite. It's all over the place.
People do see ultraviolet. It's a condition called aphakia. It's an unusual, very, very rare condition, and Claude Monet had it.
Really?
Yeah, Claude Monet had very bad cataracts, and he had them operated. He could only see reds and oranges when he had the cataracts. After he was operated, it in some way transformed his vision, and he could then see these deep purples and blue hues that were in the ultraviolet spectrum.
So the water lilies were seen by somebody with ultraviolet vision.
Yeah.
Wow. So, as artists and taking on this project, the big question for us is how do we represent colours in the UV part of the spectrum that are invisible to all human eyes and that no human has ever seen. So we've no idea what it looks like. The only way we could represent it is by showing it as a colour that we can see.
Well, the thing is, before we talk about how we might represent, I think an interesting question is why we might want to represent.
Absolutely.
And what is the value of representing an imaginary colour like that?
Well, I think what we discovered as we looked at the natural world is that there are systems of communication going on in the natural world that we know nothing about because we can't see them. We talked about bees who can see the colours of flowers that are only visible in ultraviolet and therefore only visible to eyes that can see ultraviolet. So those colours are being produced by the flowers to communicate with the bees. And the bees' eyes have that sensitivity so they can see those colours. So there's a communication system going on between flowers and bees. And similarly, but in quite a different way, we saw how the mantis shrimp produces colours in its epidermis that are only visible to other mantis shrimps. And we don't know exactly what they're communicating. Presumably, it's something to do with mating rituals and maybe other things as well. But there is a whole system of communication going on through colour.
They're signs, essentially. The colour in the animal world are their signs, presumably.
Sure. Yeah.
So,
I mean, we know birds communicate through bird song and then through mating dances and to many different ways. But these are things that just happen through colour, and through colours that are invisible to us.
If we were to attempt to see those and then represent them in order to communicate to other people that this is how a mantis shrimp, for example, might see a colour, our reasoning for doing that would be in some way to increase empathy, to help people understand the way other creatures on the earth perceive the world, even though we can't actually do it. We can only push people's imagination to do it.
Sure,
I think,
and to understand that there are other eyes looking at this earth, and that there are other forms of communication and other forms of consciousness. Although that would be a debate that's quite difficult to take on. Is that, can a creature with a smaller brain, as a mantis shrimp, see the world in any way that's similar to us at all? Because as we know, so much of our way of seeing the world is to do with the size of our brain and the size and the whole proportion of our brain, the cortex that's given over to
our perception, and how our perception influences our colours, what we actually see. For us, a colour brings emotion, principally incites emotion. I think. Well, I think
as many other things, but
of course it gives information. But one of the things that it does very powerfully, I think, is a system of triggering emotions. So red represents something, blue represents something else. I mean, I doubt a mantis shrimp would have that level of complexity.
Interesting enough, speaking to perceptive psychologists about this, speaking to Kevin O'Regan about this, and speaking to Patrick Kavanagh, both of them, and particularly Kevin, was very adamant that if you asked him, would a creature the size of a mantis shrimp have a form of consciousness, he was very adamant that no, they would not. That these would just be automatons, really.
So in that case,
even he would consider that a dog, which appears to be conscious to us, it only appears to be conscious.
And in that case, can you not say that a human's only appeared to be conscious in that case? Where does consciousness start?
Absolutely, yeah.
But I suppose the thing is interesting. So we're saying that the color system, in at least in lower animals, is a system of signaling system. So therefore, it's sending information in more or less like dots and dashes.
And clearly, other creatures respond to those signals. Like the bees respond to the colours of the flowers, and
it's receiving them.
And I assume the mantis shrimps mate because of the colours that are being emitted by other mantis shrimps. So it's a communication system that works for sure.
So, but they're close enough to animal to machine eyes. Then, if you're saying, or Kevin is saying that they're like just pure information and there's no consciousness.
So that's the other thing that we have to consider is machine eyes, because machine eyes are. There's very little argument that machine eyes are attached to machines that are conscious, at least not so far. And machine eyes really are destined to be translators. They're just translating. I'm talking about machine eyes that can see invisible light.
Machine eyes that we make, as in a detector of ultraviolet or a detector of microwaves.
So they're really just translating those invisible forms of light into light that we can see. For example, an infrared camera or an X-ray machine.
What we're looking at here are photosensitive receptors, essentially, in the human eye and then in a camera sensor.
Yeah.
So these are the same thing, except for one is nature and one is machine.
Yeah. And the interesting thing, and this is the last thing we're going to look at now in UV, and this is a very interesting thing, which is gene therapy, which hasn't been tried in humans as yet, but it's destined for eventually, presumably for people who have color blindness, and the purpose of this gene therapy is to give extra cones to the eyes.
Okay, so this is a dichromatic monkey.
Yeah, a squirrel monkey.
A squirrel monkey.
And they see in two colours. They see in blues and yellows.
Okay.
And this monkey has been given the gene therapy, which is which is meant to give it an extra cone, an extra color sensitive cone. And that extra color sensitive cone allows it to see, for example, the color that it's looking at now, which normally it would not see, would just see as grey. So this experiment is going on at present, really.
So you're saying that if the squirrel monkey can be given an extra cone to allow it to see magenta, we could be given an extra cone to allow us to see UV?
UV, perhaps.
With gene therapy?
I think it's more likely that we'll produce gene therapy for people who have colour blindness, so that they can see colours that the rest of us can see.
Okay, it's an interesting possibility, though.
But it just shows you some of the possibilities of technology and some of the possibilities of modifying and this is a continued part of the vision revolution that we've been talking about.
Well, one last thing I wanted to ask you about, because I've been hearing about the ultraviolet catastrophe.
Something that kept on coming up when we were researching ultraviolet, especially when you looked at 19th century physics, was the ultraviolet catastrophe, which, you know, being an overgrown schoolboy, that was clickbait for me.
Okay. Well, I mean, that was really just a theoretical problem that physicists were arguing about at the time. They had plotted energy levels that would be emitted from black bodies.
What's a black body?
So a black body is an absorbing body that absorbs all the radiation that comes into it, and then it can emit it in other forms.
So what, like
the sun is a black body, but also
so it's not black.
Not necessarily. No, it can glow or it can change color. The like filament in a tungsten bulb is a black body, or
so it's definitely not black.
even the sort of the element in your cooker.
But that's one. As far as I understand, they were talking about the perfect black body,
about a theoretical perfect
didn't really
black
exist.
Body.
Yeah.
And so they'd figured out that if they were, this black body was receiving energy, and as it approached the visible, as the wavelengths got shorter and shorter, the energy emitted got bigger and bigger.
So it was exponential, really, wasn't
exactly,
it? Like, and was
exponential. And so as it approached visible and then onto ultraviolet, it was approaching infinity. So theoretically, this black body, if it got more energy, it would, the energy it would then release or liberate was an infinite number or amount of energy, and that was not possible.
And that was not possible. And that was clearly not what was happening with the sun.
It wasn't. No, I mean that would be the end of the universe. It wasn't happening. So they were very upset about that, and they were really trying to figure it out. And
this is like Lord Raleigh was one of the people involved in this, wasn't it?
Yeah. I mean, I think that was really the catastrophe, was that they couldn't get their maths right.
So it was a mathematical catastrophe.
So then a bloke, a German researcher, we've actually mentioned him the other day, Max Planck.
The inventor of quantum physics.
That's right. He came up with a constant and a series of very complex equations, which we couldn't possibly go into or understand, which in fact set out that the energy levels would be related, in fact, to the resonance of the atomic resonance of these bodies, and therefore it was limited by this
in normal English, now that means that in fact it's no longer exponential.
It's limited by properties, certain properties of the body. So therefore it cannot reach.
So the curve was no longer exponential. It was like it kind of came back down. It was a bell curve.
But the important thing was that Max Planck theorized this, and then when they tested it, it turned out to be correct, and it's the basis for quantum physics. So it was a really important. I mean,
it was Planck's constant, wasn't it?
Planck's constant. But I think what's really, really important actually about that whole story, because really it's fictitious. The whole thing is that
it's a fictitious catastrophe. The ultraviolet catastrophe.
But applying your mind to a problem, even if it's a fictitious problem, led them to discover a whole series of other very fundamental truths about the universe. So that was good.
And Planck, who I seem to remember when he decided to do physics, his professor said, "Oh, don't bother with physics.
Don't bother. There's nothing left.
Everything's been done already."
Okay. Well, that's
so the ultraviolet catastrophe was nothing to do with ultraviolet, in fact.
No.